Go.
Hello, my dear students, and welcome to our first Virtual Monday. We finished our unit on the study of measurement, but like I like to do when we complete the academic portion of a particular topic, I like to look at and examine the practical portion of it. And by that I mean I like to do some labs. And I think Virtual Mondays are going to be great for just doing some virtual labs. Face to face, we would be doing this in the lab, except that even face to face is difficult to maintain social distance and to avoid, the close personal contact that favors transmission of the virus. And we've had a number of positive cases, both among faculty and students. So we need to keep social distancing and keep the kinds of interactions that are typical in a science lab, unfortunately, to a minimum. So this will be a virtual lab for this Monday. We'll have a test over this material Friday. I'll try to get all of your work graded, but you have the homeworks that inspire my questions. So you have everything you need to prepare for the test. But let's look at density from a practical standpoint with a lab that's posted to your assignments now and to your stream called the thickness of aluminum. This is a practical application of use of density to and a practical application of doing calculations to end up with a desired result. So in this lab, if you look at the procedure, it says, would you please, after a little bit of introduction, cut 3 rectangular pieces of aluminum foil. I have 3 of them here. It's heavy duty foil, Walmart brand aluminum foil. It doesn't matter what brand you use because there's an industry standard, which we'll look up on the internet in a minute. But I've labeled them 1, 2, and 3. It asks them for them to be 10 centimeters or longer. And it says, using a centimeter ruler, carefully measure the length and width of each piece. So, for example, piece number 1, when I measure it, its width is, wrong side of the ruler, 12.6 centimeters, and its length is 14. And what we want to do is measure the thickness. That wouldn't be practical using this measuring instrument. So we have piece number 1, and it is 14.0 and 12.6 centimeters in width. I need my contrasting color, there it is, so that they show up better. The second one, if we measure it carefully, number 2, is, what is that? 14.4 by 15.7 centimeters. So its length is 15.7 and its width is 14.4 centimeters. In the table, in your data sheet, it has these columns made out, maybe not in the exact way. I'll look at them on my sheet in a minute, but let's do the third piece of aluminum foil. This one is almost exactly 14. It is 14.1 by 14.5. So 14.1 centimeters by 14.5. Now remember, I told you, if you have a measurement that does not include units, it's wrong. Because I don't know, 14 what? Inches, 14 centimeters, 14 millimeters, but when we construct data tables, and there are also cases where in a sentence you might not need to put the units. When you say something like, how many centimeters wide is it? You don't need to say 14 centimeters. You already said how many centimeters. And here in my table, when you put the units at the top of a column, it refers to everything in that column. So I'm not writing my units after each measurement. The next thing it asks you to do is to mass each aluminum foil. I have several balances here in my kitchen. You could do this experiment at home if you have some heavy-duty aluminum foil, a simple ruler, and a sophisticated laboratory balance. So you might be able to find a food scale or something with enough precision, but perhaps not. This is one balance. These are both accurate to 1/10 of a gram. We have others in the lab that are accurate to 1/100 of a gram. Those are the ones I meant to bring home, but I brought home the wrong one. But let me just weigh these because I think this will be accurate enough for us. Perhaps you can zoom in on the balance numbers, but this is foil number 1. And it weighs 1.1 gram. I don't know if you can see that in the video. Foil number 2 weighs 1.4 grams. And foil number 3 weighs 1.3 grams. So 1.1, 1.4, and 1.3 grams. And that kind of makes sense. I see them getting heavier as the dimensions got larger. And I just weighed them. I'd like to say something about that balance there, and that is that this particular balance is a balance. It's not a scale. Okay, a scale is what you see the Lady Liberty, or not Lady Liberty, Lady Justice, or the Muse of Justice holding in front of the Supreme Court with the scales that balance. That is a scale. This is called a balance. It's because it has a knife edge, that piston that goes up to the weighing pan balances on, and as you put more pressure on it, more weight on it, weight is a force, as you put more force on it, then it deflects it, and that deflection is measured very accurately and related to the mass of what you're weighing. So let me now do the calculations and show you some of the things we need to do. So we're going to begin our calculations. We've got our width and length for every one of these and our mass. And two of the things we need are density and the area. The area is a calculated value. So let me just make a note about the density. It says 2.6989. Very accurate. 2.6989. And this lab is probably about 10 years old. And that's probably a pretty good number for the density of aluminum. But if you look in your Flynn Scientific Table of the Elements, the bottom right number, aluminum is a group 3 metal. Right here it says that its density is 2.90. So, this is probably off by a bit. I don't know how it's been corrected or what it's in, but we're going to use that value. We get good results with it. And the next thing I need to do is multiply 14 by 12.6. And when I do that, I get 176.4 square centimeters. I'll take it out to the 10th place because that's where it started. And I have already done these calculations, so 176 centimeters squared, or square centimeters. This one's 226.1. Of course, we would never report that in our final value. This one's 204.5. You might round it up to 205. I would round it to the nearest even number, 204. But this is just my length times my width. And if you look in your report, it says, calculate the area for each piece of foil. Please show all calculations. I really should have done this way. Number one, area is equal to length times width, which is equal to 14.0 times 12.6 centimeters, which is equal to 176.4 centimeters squared, or square centimeters. That's for foil number one. For foil number two, area is equal to length times width, which is equal to 15.7 centimeters by 14.4 centimeters, which is equal to 226.1 centimeters squared. And finally, for number three, the area is equal to the length times the width, which is equal to 14.1 by 14.5 centimeters, which gives us an area for our aluminum foil of 204.5 square centimeters. Okay. The next thing it asks you in your analysis is to calculate the volume for each piece of foil. And I'm going to do that this way, because we know volume is what? Length times width times height, but I don't have the volume. But what I do have is, I do have the density, which is equal to mass times the volume. And I know the density. I can look it up in my periodic table. I measured the mass, and so now I need to do is solve for volume. So volume is equal to mass divided by density. So my volume for sheet 1, this is question 2, my volume for sheet 1 is the mass, which is 1.1 grams, divided by my density, 2.6989 grams per cubic centimeter. Okay? So the grams cancel, that's a G. And cubic centimeters is in the denominator of the denominator.
I got it.
Oh, you're zooming in. Okay.
Mm-hmm.
I didn't think about that. So, and the denominator of the denominator becomes the numerator. So, if you do the math, this gives you a volume of 0.408 cubic centimeters. Like I say, cubic centimeters comes up. For 2, for the second one, it's 1.4 grams divided by the density, which is constant, 0.6989 grams per cubic centimeter. Cubic centimeters comes up, and I get an answer of 0.519 cubic centimeters. And lastly, for this question, sheet number 3 was 1.3 grams divided by 2.6989 grams per cubic centimeter. And that gives you a volume of 0.482 cubic centimeters. Again, you need to show your work in question 2 of your report, but these values are going to go up here, 0.408, 0.519, and 0.482 cubic centimeters. Really, these should have two significant figures. This would be 0.41, 0.52, and 0.48. If you were reporting them as your final value. Now, let me show you how to calculate part 3. So, if you go down, the next question says, calculate the thickness of each piece, show all calculations, and it says thickness is equal to volume Volume divided by the area. But let me show you how that works. Volume is equal to what? Length times width times height. Or in our case, this is height of the aluminum foil would be our thickness. So for a rectangular solid, a shoebox or a refrigerator or anything like that, if you want to calculate the volume, it's length times width times height. We've already done length times width, and that was the area. So volume is equal to the area A times the thickness or the height, H. And we know our volume, we know our area, we're solving for height, so height is equal to the volume divided by the area. And if you do the math, volume, and area, for these three foils, those values would be height is equal to 0.41 or 408 if you left it in your calculator, divided by the area, which is 176.4. This one is centimeters squared, and this one's centimeters squared, and this one is my volume, which is centimeters cubed. Centimeters cubed divided by centimeters squared gives us just plain centimeters. And if you do the math, you'll get a value of 0.0023 centimeters. That's our thickness. Okay? For number 2, height is equal to the volume divided by the area. The volume is 0.519 cubic centimeters divided by my area. My area is 226.1, a little bigger piece, centimeters squared. Centimeters cubed divided by centimeters squared is equal to centimeters. And when I do the math, it comes out to 0.0023. I was very happy with these numbers when I did this at my kitchen table. I love this experiment because it works every year. Number 3, foil number 3, the height is equal to my volume, which is 0.482 cubic centimeters, also milliliters, divided by my area, which is 204.5 centimeters squared, and that's equal to 0.0024 centimeters. So, let me add them to my column. You will add them to your column. 0.0023, 0.0023, and 0.0024 centimeters is the thickness of my heavy-duty aluminum foil. And if you look at the next one, and our table is complete now, and the final question says, calculate the percent error and determine at least 3 sources of possible error. So this was 3, I want to say. This is 4, correct? So, if you do a quick search on the internet, and I did do that, I wish I could show you. I will have a, projector set up here next time. The standard household foil is typically 0.016 millimeters, and heavy-duty household foil is typically the industry standard is 0.024 millimeters. So the standard is 0.024 millimeters. We reported our value in centimeters. There's 100 centimeters in a meter and 1,000 millimeters in a meter. So there's 10 millimeters in a centimeter. Those are the little lines on the ruler between each centimeter. There's 10 of those lines, 10 millimeters in a centimeter. So our standard is also equal to 0.0024 centimeters. Pretty close. So how do I do this? Remember I said percent error is equal to the observed minus the expected or the standard, actually the absolute value of that, divided by the standard times 100%. So what was our observed? Well, we had 3. So what we're going to do is take an average. If you add these 3 values up, you will get 0.0070. And then if you divide that by 3, we are getting 0.002333333 centimeters. So for our percent error, we observed 0.02333 minus 0.0024, and we would divide that by 0.0024, and we would ignore the minus sign, multiply that times 100. As I said last time, I'm not putting the units down because they always cancel. Centimeters minus centimeters is centimeters in the top, centimeters in the bottom. Those numerator and denominator cancel. And if you work this out, you get about a 2.7, 2.8% error. Plus or minus 3%. That's pretty good for using a simple, common classroom ruler and an accurate but not a particularly precise balance. Those balances are very accurate, but they only can weigh out to 1/10 of a gram. We could do this and get better results by doing more samples or using a more accurate ruler. There is a way to measure thickness. I have a device in the lab that will measure thickness. It's called a micrometer. You can put a sheet of paper or 10 sheets of paper or a laminated periodic table or sheets of foil or sheets of aluminum. I have copper foils or lots of things we use. And you screw it down until it closes, and you read a Vernier scale here. I have to teach you how to read a Vernier scale. This one's about 10 years old. Very precise. Measures really to 1/10,000th of a centimeter. But anyway, of a meter. So 1/10 of a millimeter. So it's really accurate out to that many places. However, the new ones are digital. You can't even buy one like this anymore. They're all digital, so you don't even have to worry about how to read a Vernier scale. We have some very precise measuring devices in the lab, but this is just, as good with a 3% error. So, the last question asks for you to name 3 sources of error, and I can think of quite a few. It says determine at least 3 sources of error. First of all, I cut these foils out with a pair of scissors, and I just kind of eyeballed them, and I can't say for sure that that's a perfect rectangle. If I measure that distance here, the same, and then here, and then here, I'm going to get slightly different measurements. And as I look at it, my cut wasn't even. I can see a little jag. I did cut this. It's not with the serrations from ripping it off the box, but it's there. And if you notice, it's got some crinkles in it. If it's all crinkled up and not smoothed out, that's going to affect my measurements as well. When I went to weigh this on the balance, you may have noticed this particular balance has a windscreen, but the foil is too big for me to use it, but wind currents, especially over something like that, can really make a difference in your weighing. You have to let your balance settle and do repeated measurements to make sure, you know, you're not under an air conditioning vent blowing down and you're measuring the force of the air blowing down. So another question is the balance calibrated? So, you know, crinkled foil, rectangles that don't have 90-degree angles, uneven cuts, air currents with the balance and uncalibrated balance, all those could contribute to our sources of error. But I think that being within 3% of the industry standard for thickness of foil, it's pretty good for a simple high school chemistry experiment measuring thickness of aluminum foil, back calculating from the density. So, some manipulated values. We have 2 sig figs in the end in our thickness. And so lots of concepts there: density, significant figures, units, unit conversions. So this is a really good lab. I wish we had time to do it together and talk about it some more. But I know you're tired of watching me and you want to get on to filling out your lab. And remember, the labs count 25%. Don't leave this one blank, because I hate to give you a 0. Because not only does it count 25% for an easy A, if you don't do it and have to put a 0 in for you, it counts 25% against you. And that's a big hit to have to take. So we'll have class. I'll have a Google Meet in class tomorrow, Tuesday. But, you know, what can I say? Welcome to Virtual Mondays. Stay safe. And I'll be back at school this week. Goodbye now, and see you in the next video.